Now that we've discussed continuous MSA, let's take a look at how well the Six Sigma team did in evaluating the backscatter gauge. Remember, this is the gauge that is used to measure the anodized thickness on the aluminum parts. So I'm going to go over to Jump and open up the Jump data table. This one is called Thickness 1. This one is in the Visual Six Sigma Datasets, Chapter 6. Okay, so this one is called Thickness MSA 1, and you have copies of this file. Okay. Don't worry about the message about an open script. Okay. So notice this is the study. They had 3 appraisers. They did 5 parts. I mean, in general, I wish they would do more, but we'll take 5. And they measure the thickness. And again, this is done with a backscatter gauge. They set a probe on the part. Then the probe sends radiation into the part and measures how much radiation comes back. And the amount of scattering is directly proportional to the thickness of the material. So once again, let's go to Analyze. Okay, Quality and Process, Variability Gauge Chart. So thickness is the response. Okay, Operator is the grouping. Okay, and by the way, this is a variability chart study. So there is where it says chart type, it should be set at variability, and then part is the response. So we run the study. Again, we can look at our variability chart. I like to connect the cell means and show the group means. Okay. So as we look at the chart, notice there's quite a bit of difference among the parts. Again, it's expected. But notice something else. There's quite a bit of variation between the 2 measurements, indicating there may be a repeatability problem. A lot of variation in the 2 repeat measurements on each part. So let's go ahead and do a gauge R&R. Okay. Okay. And let's see if I've forgotten if we used specifications or not. I'm not going to even use them. Wait, I don't actually need them. I'll show you in a moment. All I'm interested in is breaking out the gauge R&R. Notice there's no precision to tolerance or P to T ratio because I didn't specify a tolerance. But as you can see, you can look through this and see that there's quite a bit of variation. In fact, look how high the overall gauge error is. It's 63.5% of the total variation, meaning there's a lot of variation going on in the measurements. Okay, so to make a long story short, what they discovered that in doing the study, and I'll go back briefly to the notes. Okay. Okay. And I should have mentioned that they wanted an accuracy of about 1/10 of a thousandth. Okay. And what they really discovered is that the operators were having trouble positioning the probe that does the measurement on the part. So they came up with a fixturing, and they redid the study with the fixturing. And if you look at the P to T ratio, again, there wasn't a specific tolerance. The precision went down to 0.01. In other words, they substantially reduced the variation. At this point, the anodized part thickness measurement with the gauge was considered acceptable. Again, I'll just take a quick look at this. I'll open up the thickness 2 data just to show you. Again, there wasn't a specific tolerance, but we were concerned about the level of precision. So I go to, after developing a fixture to hold the probe on the part so it would be repeatably positioned, they redid the study. So again, thickness, operator is grouping, and part is again the part ID. I mean, you can already see in the variability chart that there's almost no variation between the two measurements. And if we do the gauge R&R, again, there's no tolerance, but you can take a look at the overall gauge variation and notice it's around 0.013. So at this point, they declared the measurement system to actually be capable.